In this video, we're going to discuss the second law of thermodynamics. So of the three laws of thermodynamics, the second law allows us to determine whether a process is spontaneous or not. And it tells us that in a spontaneous process, the total entropy of a system and its surroundings must increase. So it defines what a spontaneous process is in terms of entropy. So the total entropy of the universe can be described as the sum of the entropies of the system and surroundings. So we could restate the second law of thermodynamics as a mathematical equation, which would look like this. The change in entropy of the universe is equal to the entropy change of the system plus the entropy change of the surroundings. And also sometimes you'll see the entropy change of the universe referred to as the change in entropy total. So how do we determine if a process is spontaneous? Well, according to the second law, if the entropy change of the universe is positive, or is positive, then we have a spontaneous process. If the change in entropy of the universe is negative, then our process is non-spontaneous. And if the change in entropy of the universe is equal to 0, then our process is at equilibrium. So let's take a look at our second law, this mathematical equation, and let's break it down and review each of these two terms, the change in entropy of the system and the surroundings. The change in entropy of the system, we've discussed that in previous video lectures, so this is not a new concept. The change in entropy of the system depends on what's called the positional entropy. For example, if you have a chemical reaction and you form more molecules of gas, then the change in entropy of the system increases, and we can calculate that. If you have a phase change in the system, where you go from gas to a liquid, then the change in entropy of the system would decrease. So we've studied the change in entropy of the system, and we know how to calculate it using this formula. The change in entropy of the system is equal to the sum of the entropies of the products minus those of the reactants. However, we really haven't talked too much about the change in entropy of the surroundings. How do you calculate the change in entropy of all the surroundings, everything outside of the system? Well, it's a little trickier to calculate. It's easier to calculate if we know that the change in entropy of the surroundings, it depends or is related to the heat released or the heat absorbed by the system. So we're expressing in terms of the system because that's easier to calculate. So the change in entropy of the surroundings is related to the heat released or absorbed by the system and the temperature of the surroundings. So we know that the heat released or absorbed, if we have a system at constant pressure, is the same thing as the enthalpy. So we can express the change in entropy of the surroundings in terms of the negative change in enthalpy of the system divided by the temperature of the surroundings. So the change in entropy of the surroundings is equal to the negative change in enthalpy divided by the temperature. So we could say that it's proportional to the negative enthalpy change, and it's inversely related to the temperature of the surroundings. Now we like to express the entropy of the surroundings in terms of enthalpy of the system because we know how to calculate the enthalpy of the system. We can use various methods like Hess's law, enthalpies of formation, etc., to calculate the enthalpy. So we can calculate that readily if we needed to. So let's explore this a little bit more. How is the entropy of the surroundings related to the enthalpy of the system? Well, it depends on whether it's exothermic or endothermic. We know that in an exothermic process, heat is lost by the system, and of course it's transferred to the surroundings. So let's say you had a system here, and it was exothermic. Well, that means that heat is released from the system towards the surroundings. Well, if the surroundings absorbs heat, what's going to happen? As the heat is gained by the surroundings, all the gas molecules in the surroundings will begin to move faster. Not all of them, but many of them will begin to move faster. So thus, the entropy will increase. So exothermic processes release heat into the surroundings, causing the entropy of the surroundings to go up. And of course, the magnitude of this entropy change depends on how much heat flows out. If a lot of heat flows out, you'll have a larger increase in entropy. So in endothermic process, the reverse would be true. Endothermic processes, heat is lost or absorbed from the surroundings and goes into the system. So what would happen? Well, as heat is lost by the surroundings and goes into the system, the surroundings molecules in the surroundings will begin to move a little slower, and so their entropy will decrease. So the entropy of the surroundings is related to the enthalpy of the system. And we express it in those terms because we know how to calculate enthalpy of the system very readily. And again, the magnitude of the entropy change of the surroundings is related to the change in heat, how much heat flows into the system. The negative sign in front of the enthalpy is included because the enthalpy is determined from the system. We always talk about the enthalpy from the system's point of view, whereas delta S here is determined for the surroundings point of view. So in other words, a negative delta change of the delta H of the system, an exothermic process, results in a positive entropy change, that negative sign, because of that negative sign. And endothermic processes, which are positive delta H's, result in a negative delta S of the surroundings. And we just explained why that was. So now let's take a look at why the entropy change of the surroundings is proportional to 1 over the temperature. Of course, our temperature is in Kelvin. When the surroundings are at high temperatures, the surroundings have a large amount of entropy, right? So if the surroundings have high temperature, the molecules are moving faster, so the initial entropy would be relatively high. So if we transferred some heat from the system, it would result in a relatively small delta S of the surroundings. When the surroundings are at low temperatures, the surroundings have a relatively small initial entropy. So if we transfer heat, let's say from the system, exothermic process, if we transfer heat from the system, it would result in a relatively large delta S of the surroundings. To explain this a different way, let me use an analogy. Let's say you have a calm pond, a pond full of water, and it's very calm. So this would represent the surroundings at a low temperature with low entropy. If you throw a rock into a calm pond, it creates a relatively large disturbance. So at a low temperature, when we throw that, let's say we throw that that rock into the pond, it results in a large change in entropy. It disrupts the pond very visibly. We can see a very large change. However, if we had a rock and the pond was the water was very stormy and turbulent, which would represent the surroundings at a high temp, and we threw that same rock, you would barely notice any change in the pond. So it would result in a very small delta S of the surroundings. So suffice to say, the surroundings, the change in entropy of the surroundings, is related inversely to the temperature. So we could look again at our second law of thermodynamics, and we can replace this term here with delta H of the system divided by the temperature of our surroundings. So we can re-express the second law of thermodynamics as you see here. So let's take a look at a problem and see if we can solve it. Okay, we're given the following reaction, and we're asked what will be the change in entropy of the universe for this reaction, and will it be spontaneous under these conditions? Pause the video and give it a try. So here is our equation, and again we can re-express it in terms of enthalpy. So let's plug in our values here. We have the entropy of our system, which was given, and we have the enthalpy change of our system here. And again, don't forget the negative sign. And we have our temperature in Kelvin. Now, the other thing we have to watch out for are our units. Entropy is sometimes generally given in joules per Kelvin, whereas enthalpy is often kilojoules per Kelvin. So be sure they're both here in either kilojoules or joules. And then if we solve, everything's in the correct units, we get the change in entropy of the universe is positive 2.65 kilojoules per Kelvin per mole. So for this reaction, we had a positive change in entropy of the universe. So that would tell us that this reaction is spontaneous under these conditions. Now again, you could have put that in joules, that's fine. So the second law of thermodynamics allows us to determine whether a reaction will be spontaneous or not. Let's take a look at one other problem. This is a discussion type question. Explain why water freezes below 0 degrees Celsius in terms of the second law of thermodynamics. Now I want you to pause the video and give it a try before you see my answer. Pause the video and write down what you think the answer might be. Okay. So let's take a look at this. We know that water spontaneously freezes below 0 degrees Celsius. We know that. So therefore, we also know that for this process at these temperatures below 0, the change in entropy of the universe must be positive. We know that based on the second law. The water molecules become much more ordered as they freeze. So the system is decreasing in entropy. Right? So the water molecules are going from a liquid to a solid phase. So the system is decreasing in entropy. So that's a negative sign. We don't know the magnitude, but we know it must be negative. The process also releases heat. So as this process, as the water cools and freezes, it releases heat as we begin to form stronger intermolecular forces. And so this heat is transferred into the surroundings. So we know if the process is spontaneous and the delta S of the system is negative, we know that the delta S of the surroundings must be positive. It must be increasing in entropy because it's absorbing heat from the system. So this process of freezing water is exothermic. So looking at this, we know that this must be positive because it's spontaneous. And if the delta S of the system is negative, we know that the delta S of the surroundings must be positive. And the sum of these two must be positive in order to make this value here positive. So we know that the delta S of the surroundings must be greater in magnitude than the delta S of the system. So to sum this up, we could say the entropy can be viewed as a dispersal or randomization of energy. The freezing of water is an exothermic process, so it releases heat to the surroundings and thus increases the entropy of the surroundings. The process is spontaneous at or below 0 degrees Celsius because the increase in entropy of the surroundings, and this is important, the increase in entropy of the surroundings is greater than the decrease in entropy as the water freezes. So we want to basically appreciate the relationship between the delta S of the system and the surroundings in order to explain why a process is spontaneous. So take a look at this. Be sure you can do calculations as well as discussion questions related to the second law of thermodynamics.